Hi everybody, welcome to the 11th video of module 9, and here we're going to talk about the fully connected layers. So after we are getting the output of the pooling operation, what next? You can have multiple bunch of convolutions and the pooling layers, so on and so forth. But after that, you can convert it into a 1D array with the help of flattened layer. It's going to act like the input layer that you are having in your dense neural network. After that, you can have multiple hidden layers depending on how much you want to decode the features that are present in the flattened layer. And then finally, you are having the output layer depending on what type of task you are solving. So all of these kind of things we are going to cover in this video in a proper detail. So let's get started. So given any image as a part of the input to your convolution neural network, convolution layers are going to extract the features from the image and produce a respective feature map. Then it's your choice if you want to implement a pooling layer on top of the convolution layer. In case if you want to reduce the whole size to the half, the output of the convolution layer, you want to reduce that output to the half and then focus only on the necessary information or the most important information. And then again, you can have a convolution layer, then again a pooling layer, so on and so forth. It always depends on the complexity of the input image. If the input image is pretty much larger and very much complex, there are a lot of features present in there, then you can have a bunch of convolution layers followed by a pooling layer. And typically you will see we are using max pooling over here to focus on the pixels with the maximum values. And this will represent as the one of the most important features. But at times, let's say if you are dealing with those type of pixels where your features are present, where there are darker regions, you can go with the minimum pooling or the mean pooling. If you are confused, you can also go with the average pooling. So that part is clear, right? We had the convolution layers to extract the features, and then it's our choice if you are really focusing on the most important parts by even reducing the overall output shape that you had in the output of the convolution layer. So let's say after you have this kind of decision, the next thing you need to decide is how many convolution layers and the pooling layers you need to have. It's completely your choice. You can come up with, let's say, a series of convolution layers, then a pooling layer, then again a series of convolution layers, and then a pooling layer. Again, it depends on the complexity of the input images. More the features, you will need more convolution layers. And if you are really focusing on reducing the whole size of the convolution output to the half and focus on the important part, you also add a respective pooling layer. But let's say after all of these things are done, the next thing you need to do is you need to know that whatever output that you've got at the end, okay, the more deeper you go into the CNN, the more complex features you are having. Now, if you want to have more understanding on top of that, you always flatten that thing and convert it to a 1D vector that's going to be connected further to the hidden layers and then the output layer. So this fully connected layers is pretty much similar to what we had studied in the previous module while looking into the multi-layer perceptron. It's a feed-forward network, by the way. So flattening this feature map that we have got, let's say from the convolution layer, or if you're having a pooling layer, once we flatten that, it produces this one-dimensional vector, which we further feed it to the MLP or the feed-forward network. And this feed-forward network takes this flattened features and applies some kind of activation and returns the output. This output stating whether the image contains whatever kind of category we had in the output layer. So again, what is the task or the meaning of having a lot of dense layers over here? You can also have one flattened layer and directly the output without any kind of dense layer in the middle. So over there, let's say if the model is not performing well, you can try to then include one dense layer in between the flattened layer and the output layer. See if the model is improving. If the model is improving, you can try to have one more hidden layer in between the flattened and the output, and then see if it's still improving. If it's still improving, you can do this kind of trial and error until you get the results that you want to achieve. So that's exactly how a whole CNN goes. You have convolution layers connected with pooling layers, and all of that once done, you flatten that out into a 1D vector, and then finally have this hidden layers and the output. So what's the whole benefit of the CNN? With the help of the convolution layers and the max pooling layers, you are reducing the whole shape before flattening it. And because the shapes are reduced and having the most complex features from the input image, now if you flatten it, the number of inputs that's going to connect it to this kind of dense layers are going to be very much less as compared to if you directly use the MLP. Over there, the whole input image is a large thing altogether that you're going to convert it into a 1D array. Then it's going to go into the this kind of dense layers, the network over there will be very much complex. There will be a lot of parameters over there as compared to a CNN. In CNN, the number of parameters has been decreased because of this whole way of dealing with this image data, and therefore it's more efficient as compared to a normal MLP model. So there you go, guys. You are now having complete idea about how the CNN architectures looks like and how it really functions.